So we're going to do this with two laptops. The one laptop is going to be your questions, so I can see your questions. And the other one is for me to do the presentation. I carry two laptops because I've got a Mac. So it'll be more fun if you ask questions, and I can then show this question and we can answer the question together. This is a fairly interactive talk, and I'm going to be doing lots of coding. So if you get lost on the coding, I apologize. We don't want to get you lost, but some of it might be a bit tricky, because the subject matter is itself a bit tricky, right? Thread safety. And there are three main classes we're going to look at: Phaser, StampedLock, and Var Handle. So I'm not catch-up. My name simply happens to be the same as a very large company, which makes it kind of difficult to register domain names. Heinz.com it's gone already, right? If your company loves you, only if your company loves you, if your employer loves you, they might be willing to let me come and do courses at your company, but only in that case, right? If they don't love you, then they won't ask me. I also have a surprise, because I do love you. tinyurl.com/GeeCON-Phaser. If you get that before lunch, you get a very nice surprise. Now, if you're watching the recording, you will get a surprise, but not as nice as the people who got up really early this morning to get here by 9 o'clock, and I really appreciate that very much. So let's look at the first class, Phaser. What this class does is it allows threads to coordinate with each other by phases. It's in a structure similar to CountDownLatch and CyclicBarrier. Now, CountDownLatch is really, really simple. It's basically we're counting down until we hit 0. And before it's 0, then the latch is closed. Once it hits 0, then it's open. So very, very simple. Phaser is a bit more complicated in the interface, but once you start using it, it becomes simpler. And I'll show you some demos of how these two classes compare. One of the things with Phaser is that you can register and deregister parties over time. And this is similar to what you'd call count in Phaser or parties in CyclicBarrier. It is also one of the few classes which integrates with the fork joint pool. It's a relatively new class, new as in Java 7, right? Which is, of course, not that new, but, well, it's newer than Java 5, right? And fork joint pool was added in Java 7. So there are only a few classes which really integrate with fork joint pool. One of them is Phaser, another one's completable future, and there's, I think, one other one now which is also there. But which means that you can use it safely within any constructs which happen to work within a fork joint pool. So, for example, if you need to block whilst inside a parallel stream, Phaser would actually work. So I've got this little demo that I want to try out. It's in my GitHub repository, Modern Synchronizers, and we're going to try and get this working. Now, the demo is a little bit tricky, a little bit complicated. What I want to do is I want to have some coordination between a bunch of tasks. What I want to do is I want to have tasks starting at the same time. Now, it's actually quite tricky to start tasks at the same time. So the way that my demo works is like this. I've got a co-joining task. The co-joining task takes a runnable, which is the joiner. And the joiner is going to be used in order to coordinate for everybody to come to the same position at the same time. And then we're going to have the actual task that gets run. So you can see here that the start time is measured in system nanotime. Then I start the task, and so what I then can see afterwards is how well did that work? How close did these tasks get started together? You know, is there a microsecond difference or nanosecond difference or millisecond difference? That's what I'm going to try with this demo. The tester is a little bit on the complicated side. What I do is I basically I'm going to submit the job, run it with the number of tasks, and the number of tasks on here is going to be the number of parties is going to be the number of available processes divided by 2 minus 2. Now, why minus 2? When y divided by 2, first of all, on my laptop, I've got 6 cores, but it's 12 hyperthreads. Now, the hyperthreads don't really help you very much with parallelism. So what I'm going to do is I want to have actually only 6 threads, but I also need a thread for coordination, or maybe 1 extra thread. So basically, you will be able to run this on a 4-core machine, but not on less than that. So the number of parties is going to be on my machine 4. All right, so that's what we're going to do. Now, I'm going to try different co-joiners, and then once I've written them, you will see how that works. If I code it correctly, assuming, because it is a Thursday morning at just after 9, and normally my brain only kicks in at about 11. So, but we'll try. Now, the first one is to do nothing, right? So the waiting doesn't wait at all, and the signaler doesn't signal at all. So there's no waiting, there's no signaling. And if you look at the co-joiner, I haven't shown that yet. Let me show that quickly. The co-joiner is an interface which has run waiter and run signaler. So to do nothing, you don't actually have any coordination. And so you're just relying on the operating system and the Java virtual machine to hopefully start the threads relatively close together. We'll see how well that works. Then we'll do a volatile spin co-joiner. And what we're doing here is we're putting inside a volatile variable, volatile Boolean, ready equals false. And then inside the rate, we say while not ready. Sorry, this keyboard is unfortunately not that wonderful. Run signaler will say ready equals true. So what this will do, it's going to have 4 threads. We're just going to spinning. And then once you say ready equals true, right? Yeah, once they're ready equals true, then those threads all start. So they're all hot and they're ready to go. So that's quite an easy way of doing things. But of course, if it takes a long time for these threads to all reach the same position, you're going to have all these threads just spinning and wasting CPU cycles. And there's something you can do about that. There's actually something called thread.onSpinWait, which is new since Java 9, which is sort of the recommended thing you should do if you're going to do some sort of spinning over here. So we'll put that in as well. It actually doesn't seem to make any difference in my machine, but maybe in the future it might make a difference. All right. And if you have any questions, please pop them into the slido.com, GeeCON 2019, and I'll see them on my second machine here. Let's try wait notify. We all know wait notify. So we're going to have a private final. We actually let's in fact have a Boolean as well ready, and we're going to start with false, and then we're going to make this synchronize the waiter, synchronized run waiter, and we're going to say while not ready, and we're going to say wait. Right, so we're going to keep on waiting. Now, you notice, of course, that here there's interrupted exception. It's underlined with red. And I know that the darkular color scheme is incredibly popular, but for me, it's far more difficult to really spot the mistakes. Here, it's really obvious where the mistake is, but that's just me. I think that in the long term, the darkular is easy on the eyes, but it's just quicker like this. So we can see that there's an exception, and we keep on getting this exception. What are we supposed to do about it, right? Because the run waiter method doesn't allow me to throw an interrupted exception. I'm saying I want to wait until everybody's here. If you get interrupted, well, that's your problem. I don't want to know about that, right? We need to actually hide that from the user. So, okay, I'll deal with it in a moment. The run signaler does this. It says synchronized void signaler. Then I'm going to say ready equals true, and I'm going to say notify all. And you should always use notify all rather than notify. I won't go into why here. Now, how to do this? Well, what you can do is the following. You can say while true, while not ready, wait, And then what you do is you try catch that. Now, what I'm saying is that if someone interrupts me whilst I'm waiting for this to happen, I want to remember that I was interrupted, but I still want to carry on waiting until all the threads are at the same place. And then I'll exit from there in the interrupted status. I need to make sure that I keep that consistent with the way that the other mechanisms work, so to keep it all the same. So I'm going to say Boolean interrupted equals thread.interrupted, which also clears interrupted status on the thread. So thread.wait over here, if I get interrupted, I'm going to say interrupted equals true, and I'm simply going to continue waiting. Once I come out of the wait, I'm going to say, if I was interrupted, then I'm going to do a self-interrupt. I'll interrupt myself. All right, so this is the wait notify cojoiner. And I'm not sure how well it'll perform, because when I wait, I actually have to suspend the thread. And similarly, when I say notify all, the threads they all wake up, but now they have to, one by one, compete for the synchronized, and then they can start up. So we'll see how well that compares to the other mechanism where they're simply spinning and looking at the volatile value. All right, as I said, any questions, pop them onto Slido. The next one was a countdown latch. And here we're going to simply have a private final countdown latch. Let's make it equals countdown latch of 1. Run signaler is going to be very easy. We say latch.countdown. And run waiter will say latch.await. So all the waiters will wait until the latch has counted down to 0. But here's another problem, right? Because, again, we've got this whole thing with interrupted exception. We have to manage that. So let's do the same code as we did before. Try catch. But now we need to do a little bit more, because we have to say Boolean interrupted equals thread.interrupted. And then we need to put this into a loop. Where's the loop? Number 3. While true. Latch.await, return, right? And interrupted exception will simply say interrupted equals true. And I need to here also say if interrupted, then current thread.interrupt. So it's a little bit, as you can see, it's a little bit tricky to get this right. A lot of coding to get this right. And it'll be interesting to see how this performs against, for example, the wait notify. The wait notify is a slightly more primitive mechanism. Is there any mistake here? No mistake? Okay. Now the phaser is another mechanism. Over here, we're going to make a phase, a private final phaser equals new phaser. And one of the things which I want to do is to make sure that that I actually have they really start at the same time. So what I'm going to do is I'm actually going to say take the parties that I had before plus 1, and I want to make sure that all the weights are at exactly the same place. So the run waiter is going to do the following. We're going to say phaser.arrive and await advance. That's for the waiters to all arrive at the same place. And then once they're all at the same place, then they can advance. And the run signaler would be the last one to actually notify them all. This was, say, phaser.arrive and deregister. Arrive and deregister means that after that, the number of threads which are waiting would actually be one less. So you could have phases going through. Right. So you can see this code is, of course, like the really, really simplest. It's actually even simpler than the volatile spin cojoiner. And if you run the code, let's run it with the test all. This is going to be doing a whole bunch of tests. And then we'll see how the things compare. Oh wait, so that's the wrong one, wrong test. That's not the right test. I thought it was wrong. I meant to do this one here. So let's try that again. So what this does is it runs it a few times a test, and it looks at the number of nanoseconds that we had to wait. And it runs it quite a few times, and then what it does is it actually counts what is the total time that we had to wait after all the tests have run through. And what's quite interesting is if you look at the non-joiner, here we're relying on the operating system and the virtual machine to do its thing. And the maximum was 57 microseconds. This is in nanoseconds, right? So 57 microseconds was for none. That was the longest wait, which is not too bad, actually. And the total, if you add them all up together, is 218 milliseconds over that test. So this meant the max, what that means is if I have four threads arriving, and they're all called nanotime at the same, well, they're all called nanotime, what's the maximum difference between the first and the last? So the maximum difference was 50 microseconds here, 57. If you look at this one is a better one. So 50 microseconds was the biggest difference between the first and the last, which isn't that much. And then the total, if you add up all these, it was 211 milliseconds. The wait notify, the maximum was 227 microseconds. It's actually worse than not doing anything. And the total is 400 milliseconds. The CountDownLatch cojoiner, 54 milliseconds. Again, it's not much better than doing it with nothing. And 400 milliseconds again. The volatile spin joiner, we would have expected that to be better than wait notify and the CountDownLatch. We expected that to be better because all you're doing is just spinning, keeping the threads hot. And then as soon as you put the volatile true, we can all exit from here. And there the total is 91 milliseconds. And the phaser codejoiner is actually the best. It's really complicated code, but it performs the best. So you can see the maximum was 18 milliseconds. Here it was actually only microseconds, the worst, the highest ratio between start and end. And we can see the total is like 5 milliseconds versus the wait notify or the none or the CountDownLatch. So it's really good for something like that. Yeah, Jaya Match for measuring time, if no, why? Good question. I use Jaya Match for lots and lots of different things, but not for this one. I used it yesterday for the strings talk. Sometimes it's not the right tool. All right, so that is phaser. Any questions about phaser? All right. The next class we want to look at is StampedLock. Now, StampedLock has been around since Java 8. And when StampedLock first came out, I started speaking about it pretty quickly. And after a while, I wanted to know sort of what is it really about. And luckily, Doug Lee was giving a talk about StampedLock. Or he gave a talk about concurrency at some keynote somewhere. And you know, Doug Lee is the guy that wrote StampedLock and a whole bunch of other very clever classes. So I found his video on YouTube, which is kind of weird because it was mirrored, so like left to right and so on, kind of weird. Some weird movie. But I found it somewhere. And he was talking first about long adder and stripe 64, and then he got to StampedLock, and I thought, great, now I can learn something. And he put up my slides, so that was kind of disappointing. I didn't learn anything from him. Difference between phaser and cyclic barrier, great question. So cyclic barrier has a constant number of parties. So you can't change the number of parties. So with cyclic barrier, once you like, if you want to change it dynamically, you need to create a new cyclic barrier. There is something which is similar between cyclic barrier and phaser, in that in both cases you can have a runnable that you call each time you go through a cycle. Also, the phaser actually knows what phase it's in. That's what the name phaser comes from. So the phaser has a lot more features than the cyclic barrier. All right, let's get back to the StampedLock. So the StampedLock is a Java 8 synchronizer. It allows you to have optimistic reads as opposed to only pessimistic reads. If you take, for example, reentrant read-write lock, It's also got reads and write locks, but the read locks are all pessimistic. And what pessimistic means is that I can't read while somebody else is writing. I can't do that. That's what pessimistic and optimistic means. It's not reentrant. This is not necessarily a feature. It also, and the way that the reason you'd want to use it is if you've got multiple fields and you've got some invariant across those fields, then you could use this class because you can enforce the invariance. But sometimes it's going to be really difficult to write the code. So we'll do a couple of demos to try and get that to work. For simple classes, using a simple synchronized and a volatile read is going to be easier and probably faster as well. Something else that's interesting is that the stamped lock doesn't know who locked it. So when you say StampedLock.lock, you actually get back a number that you use to unlock it. So if you want to protect the resource, you can actually do that, even in an asynchronous coding environment. So you could lock a resource with a stamped lock, get the lock number, and then once you finish with the resource, you can unlock it again from another thread. Doesn't matter which thread it is. And that's, again, it's a feature, which it wasn't really supposed to necessarily be like that, but it just happens to be like that. Now, the stamped lock has 3 different modes. The first is an exclusive write. This is like a write lock, exclusive lock, pessimistic exclusive lock. And if you say StampedLock.write lock, you get back a number. This number will never be 0. 0 would mean you didn't get the lock. So write lock will always block until it gets it. And then you can also say try write lock, then it might get back a 0. You can also try and convert a read lock to a write lock with try convert to write lock. Now, if you remember reentrant read write locks, the reentrant read write lock cannot be upgraded from read to write lock. But this one can be possibly upgraded to write lock. Then we've got the unlock write, and that needs a write stamp. If you put something else, that's not going to work. And a whole bunch of other methods I've left out, just, similar to read write lock. We've got the non-exclusive read, pessimistic as well. We've got the long read lock, gives back a number, it won't be 0. We can convert a write lock to read lock, or an optimistic to a read lock with try convert to read lock. We can unlock a read, and we can unlock generally, which would be either for read or for write. And now the third mode is when you have optimistic non-exclusive read. Now this is the big one. That's why you'd want to use it. The stamped lock, you can say try optimistic read, and I'll show you an example of an algorithm of that in a moment. Try optimistic read might give back 0. It might give back 0. If somebody else currently has the write lock, then it would give back 0. But hopefully it won't. We're being optimistic. And it would return true if the stamp is non-zero. The validate afterwards would return true if the stamp is either non-zero and no write lock has been requested in the meantime. So it basically is a check, has anybody asked for the write lock in the meantime? It's not a guarantee that somebody has actually written, but even if somebody has tried to write, you would say false on the validate. Let's have a look at some code. So this is the algorithm, and we'll look at it one bit at a time. First of all, we're going to try get an optimistic read. And this gives back a number which can be 0, it might be 0, but we don't check whether it is 0. That's one of the key things, is we want to carry on as quickly as possible. We don't want to wait and do any code or as little code as possible until we get to the validate. The shorter the path between the optimistic read and the validate, the higher the probability that you'll actually win the race. We then read the state into local variables, current state 1 and current state 2. And after we've read it into local fields, then we need to validate the stamp. So the validate here might return true if nobody has tried to get a write lock in the meantime. But if somebody has asked for a write lock in the meantime, or if the stamp is 0, then it'll come back with false. And in that case, we can get a read lock. We would now basically go for the pessimistic read lock. And of course, what you could do is you could write a loop to try it a few times. Just say 1 to 5, try and do optimistic read. If it doesn't work, then you downgrade to a pessimistic read. And you should actually, in your program, win at least 10%, or you should win 90% of the time. There should only be 10% of the time where you have to downgrade to the pessimistic read. All right, so what we do is we then get a read lock, normal read lock. We read the state into the local state, and then we unlock the read. And then finally, we can use that for our calculation. Any questions? Any questions, pop them in, or put up your hand and shout it out. All right, so I live on the island of Crete, and people ask me why do I live on Crete and not in Poland. Well, I do like Krakow very much, but my wife is Greek, so we live in Greece. That's how it works, right? I think James Gosling is married to a Polish lady. I think he is. And we were speaking to him once, and we said, "Why don't you live in Poland?" He's like, "No." He's happy in California. So on Crete, we had a crocodile, a live crocodile walking around. And this crocodile became like a feature, right? What happened is, on Crete, you can buy almost anything you want. Like for an AK-47, no problem. Anything. Anything you want, we've got. You want to buy a tank? We've got a tank. No, we've got everything, right? And so you can buy any sort of pet you want, right? It's all available. It's of course all illegal, but it's all available. So somebody probably bought a crocodile because it's quite fun having a crocodile, And then after a while, this crocodile kept on growing and getting bigger and bigger and eating up all the chickens. And they said, well, you know what, let's just leave it out into the wild. So the crocodile was walking around the countryside in Crete. And they tried to catch it, but they didn't manage. They set traps, and they wouldn't cover the traps because it had so much food anyway, So it didn't need to, I don't know who it was eating, but it didn't need to eat the bait and the traps. So eventually, it does get pretty cold in winter, and it passed away. But it had a name, Cephas, and, so this crocodile. Now, how is this relevant to StampedLock? Well, let's say I want to move from one position to another. I want to move from 0, 0 to 5, 5. And I want to go diagonally from 0, 0 to 5, 5. So we don't ever want to be in a position where we become crocodile food. So this is good. Cephas is down there, and we're going from 0, 0 to 5, 5. We're all happy. But if we accidentally see an intermediate state of 5, 0, we become crocodile food, which is not so pleasant, I believe. Never tried it, but I don't think it's nice. So that's what we want. We want to make sure that we never see the intermediate state that might be invalid. And let's have a look at how you would do this. So let's go and look at this example here. Let's close that. Close that and go to. So here's my position. And this is, and I've actually done this all wrong. I thought I must have made a mistake here. Let me just do this again. I'll just type it in for you. Right. So this is a position, and basically the way that you'd normally do it is you would have synchronized move by would be x plus equals delta x and y plus equals delta y. And then distance from origin would say return, we're doing COBOL here. Synchronized would be return math.hypotenuse x, y. So that's how you would normally write a position class. So if you want to have from move by delta x and delta y, we're synchronized, it's moving together. And then distance from origin would be math.hypotenuse of the two. Now, if you want to do this with StampedLock, the way that it would look is like this. You'd say private final StampedLock equals new StampedLock. And notice you can't make it fair, because fairness is overrated. It doesn't really work that well. And then the move by, we're going to wrap that with a right lock. We're going to say long stamp equals SL.WriteLock. That's a pessimistic exclusive lock, try, and finally SL.unlock right of the stamp. Okay, so that's how you do it. Now, the right lock will always come back with a non-zero value, so you're guaranteed of that. Then I've got distance from origin. And distance from origin is a little bit more complicated. Here we need to have this optimistic updating here. So we're going to say long stamp equals SL.try optimistic read. It's not a lock, of course. Nothing's locked at all. And at the same time, somebody else can go and write it if they want to. And then we can do this. We can say, is it a long or a double? It's double. So we're going to say double current x equals x and current y equals y. And then we can say if SL.validate of the stamp is false, then we need to downgrade that to a pessimistic read lock. So we're going to say stamp equals s.readlock, try current x equals x and current y equals y, and finally SL.unlock read of the stamp. And then when we say hypotenuse, we're going to say current x, comma, current y. So that's how we're going to do the actual hypotenuse. So we read it into local variables, and then we do the hypotenuse calculation with the local variables. Is it possible that JIT reorganizes the code so that try-optimistic read will be moved after assignments? No, this is not possible. This is a volatile variable. State is volatile. And because state is volatile, it can't move that down. It has to stay in that place. And with validate, you've got an acquire fence as well. So this is all thread safe. So it's not possible that the try-optimistic read comes lower after the read. What is possible, though, is that when you are reading, you might be pointing to an object which changes. So the object itself might change. So it has to still be careful when you're doing the reading. Thanks for that question. All right, so this is how you would write it. And one of the things that you often want to do is to actually see, well, let's try optimistically a few times before we give up on that. So we'll, in fact, let's just run the test and see how this runs to make sure it actually works. So let's run that first of all. And what I'm measuring here is the compute time over elapsed time. What's interesting here is that your user time is really high. It's like 99% is user time. So and the system time is almost nothing, the system time here. Again, you could do this with Jaya Match, of course, but I want to do something very, very specific, so that's what I'm doing here. And so what I'm finding here is that the move, both of these, the best values, for example, the move was 55 million times, and distance 10 million times, right? But what we're looking at here a lot of is the user time over elapsed time. It's basically we don't have a lot of system time. If you did this test with normal synchronized, in fact, let's just add synchronized on top of that, then you should see a lot more system time. So we're going to make it also synchronized. I don't want to take away the other code because I spent so much time writing it. But you'll see now that the system time over elapsed time is going to go much higher. So you can see here 16% system time, 30% system time, and your user time over elapsed time goes down significantly. So you're wasting lots of CPU cycles on context switching. We don't want to do context switching if we can avoid it. All right, so you can see there we go. It's a slight difference. Get rid of the synchronized. We don't want to have synchronized. We want to get rid of that. All right, so that's the first example. What we could also do here is we could, with this from origin, try a few times. And you could do that by basically putting a loop in here. So you can say, go from 0 to 5, for example. Probably want to put that into constant, retry count, and then we want to do the optimistic read stamp in there. And do you know that there's the thing? Do you know that you can actually do goto in Java? Yeah. So what you can do is you can say out in front of that. And then you can say, if SL validates stamp, we're going to put the current up here. Sorry, this must be slightly wrong. Copy this up here. Current, no, sorry, this was supposed to be at the top here. Current x, y, like that. Current x, current y. And then we'll say current x equals x and current y equals y. If SL valid has stamp, then break out. Okay. And then we're going to do this optimistic reading, the pessimistic reading. We'll then do inside that code over here. So let's just connect this up here and like so. So this actually will work as well. So here I've got basically a for loop, 0 up to retry count. I'm calling optimistic read. Current x equals x, current y equals y. If validator stamp is true, I break out. It's like go to the end of that code block, and then I return math.hypotenuse. And if I don't within the 5 count, then I end up returning with math hypotenuse. Right. So this is some coding examples, and there are lots of other idioms you can use as well. There's one fairly large example called int list, but this is a lot more involved, and I rather want to look at something slightly different over here. And what I want to look at is I want to take this code that I've got with my position and copy and paste it into another example. So we'll do it over here. Right. So let's get back to here. So we've done that. Now, I want to look at the last construct, which is Var Handles. And Var Handles were added in Java 9. They gave us this thing called Unsafe in Java, I don't know, 6 or something. At some point it arrived. It just arrived out of nowhere. And in the old versions of Java, they used to use something called atomic field updaters. So they'd have like a normal field, like for example, a concurrent link queue that have a normal field, and then it'd have an atomic reference field updater to update the beginning and the end of the queue. And this atomic reference field updater suffered from amnesia, right? Now I've really got a problem with amnesia in a way, because if you tell me your name, right, it doesn't matter if it's in Polish or in English or anything, I will forget it almost instantly. I've got a really bad memory for names and for faces. I was in Warsaw a couple of years ago with my family. My wife and my 2 younger children came along, and my little one, who's now 6, still remembers the sweet shop in Warsaw where she bought these special sweets. But that's all she remembers is the sweet shop. But we went, I gave a talk with, I can't remember who it was, somebody, Roach or somebody. It was, you know, I gave a talk. Well, as I said, I've got a problem, right? And after the talk, this guy comes up to me and he says, "How's it going?" I'm like, oh crap. Who's this? I had no idea. I thought I'd seen him somewhere, but I really didn't know who it was. And so I used this trick. My wife came up and I said, "Hi, I want to introduce you to Helene." And she said, "Yeah, I know him. He's Andre." I'm going like, "Where do you know him from?" And he came to Crete, and he spent a whole week with us on the beach, talking and eating, and I didn't even recognize his face. let alone know his name. So I'm already apologizing for the problem. Now, atomic reference field update is a bit like that, right? Basically, you use it, and it says, well, are you even allowed to do this stuff? And then it checks, can you do it? And then you use it again, it says, but who are you, and are you allowed to do this stuff? And it checks, can you do it? And then you want to use it again, are you actually allowed to do this? And so every time you call it, it checks, are you actually allowed to do this, or you're not allowed to do this? So that's sort of how that works. And so it wasn't as fast as going directly to the memory. And so in Java 7, inside the concurrent link queue, Sun Oracle, whoever did that at the time, changed it from atomic field updater to unsafe. And of course, because everything is visible to us programmers, we look at them and go, oh, that's interesting, so we can actually use unsafe. And of course, you're not supposed to because it's in sun.misc, but people just do, right? People just started using that. And so we use it for all sorts of clever things. And this caused a problem because with unsafe, you can access memory directly. So what they did was they tried to move this out of harm's way. And they gave us something that is as fast as unsafe. And they've also now actually made atomic field updaters faster, so that actually sort of defeats the purpose of using that. Now, with that, you can have different modes of reading and writing values. The strongest mode is get and set volatile. That's a very strong one. With get and set volatile, you're guaranteed to see the correct value. And when you're writing it, it's actually going to wait for everything to be written before it returns. So writing and reading on volatile is quite slow. Then we've got get acquire and set release. And this is quite useful when you've got a single thread which is writing and multiple threads that might be reading. And we use this, for example, if you look at JC Tools by Nitzen Wackart, he's got a whole bunch of really clever cues based on the work by Martin Thompson, mechanical sympathy, and there we use acquire release a lot because we want to have cues which work as quickly as possible. And then set opaque, get opaque is a new version, a new a level that we didn't have prior to Java 9. What this does is it guarantees only a very few things. It guarantees that your writing is going to be atomic. So if I write a 64-bit value, it's going to be written as a single operation. It's not going to be written as 2 half of 64 values. So that's important. It also tells you that whatever you write is going to be visible at some point in the future. But you don't know how long it will take. It might take 1 microsecond. It might take 1 millisecond. It might take 1 year. You don't know. So set opaque, get opaque is not useful for inter-thread communication. It might be useful for logging, but not for communication. So you can't write a queue based on set opaque and get opaque. And if you do write one and it works, your test is broken because it doesn't work. And then get set plain, that's just like normal writing and reading. All of these modes are also available now in the atomic classes, atomic integer, Boolean reference, etc. And then you've got compare and set, which is like your normal cas. That returns a Boolean. And then there's a new one called compare and exchange volatile, which always returns the value that it found. Oh, no, we don't need that. We don't need that particular poll. Somebody just put up a poll for our section. We didn't want that. Okay, don't know what the poll's doing there. All right, let's have a look at the position class. And we've got the position class now here with, oh, that's the wrong one, wrong button. Position class here with our StampedLock. And the StampedLock we saw was fairly quick. Let's just run the code here to see what sort of performance we get from that. And with the StampedLock, the good thing is that your move and your distance from origin wouldn't interfere with the move. All right? So this is sort of it's running a few times. Just want to get it finished. We look at the next one. Here's another reason why I'm not using Jaya Match for this, is Jaya Match will need a long warm-up. So I can't really do that as a demo here. I can only show you the results, not so much fun like seeing the answers here. So I'm going to just copy and paste these values in here. So we have those. And then we're going to refactor this to use Var Handles. Now, let's get rid of this StampedLock. And we're going to do this all with Var Handles. So instead of having two different fields, I'm going to put in there a double array, x, y, and equals, in fact, let's make it here. Inside, we're going to say x, y equals new double array, x, comma, y, like so. That's my position. And then move by is going to simply write a new double array onto that. How do you do it? Well, it's going to be with compare and swap. So what we're going to do is we're going to create a var handle for that. So private final static var handle xy. Normally we name it by the field, but uppercased. That's how we normally name it. We normally put the var handle at the bottom of the class. And in the static initializer block, we say this. We say xy equals. Now, for some reason, they wanted to call it method handles. It actually, at one point, there was a class called Var Handles in one of the beta releases of Java 9, but they took it out and they just used method handles dot lookup. And what this does is it finds out who is this, right? We bought a plot of ground in Crete, and the people who are selling it wanted to know who are we, because if we are not the right people, they won't sell it to us. Doesn't matter how much money I've got. So I find the var handle with the name, with the class on which I need to find it, which is going to be position.class. The name is going to be xy, and the type is going to be a double array.class. Now, what this does is it's going to possibly throw an exception. So we're going to say try catch, and both of these exceptions are reflective operation exceptions. And if we get those, we simply say throw new error of E. That's it. So that's what gives me the method, the var handle, the standard way of doing it. So the move by is going to be double current equals xy. And in order to do that properly, we need to make this volatile. So volatile here. Double current equals xy. And then we're going to say comma next equals new double array of size 2. That's where I'm going to go next. And then we're going to say do. And I'm going to say next equals, or next naught equals current naught plus delta x. And the same thing for next 1 equals current 1 plus delta y. And in fact, I need to actually say current equals xy inside here. I don't think it can do it over here. Like so. While not xy.compare and set, and it's going to be on this, so the object, current object. I'm expecting it still to be equal to current. I'm trying to set it to the next value. I'm going to keep on trying until I'm successful. And once I'm successful, exit from the void. So that's the move by. It's a little bit more complicated, but it's not too bad. The distance from origin is pretty easy. We have double array current equals xy. And then we can simply say current naught and current 1. And we're sure that we are not going to interfere here. Let's run that and see how that performs. Okay. So my my distance from origin should be much better. It's just, one volatile read, you're done. Very, very quick. Of course, there are a whole bunch of things that happen underneath it. Now, as I'm seeing here, looking at the questions, for some reason they managed to put a poll up, which is incorrect. And I can't see any other questions, so you're going to have to ask the traditional way. And time's up actually anyway. So how do we compare? Let's look at the best values, 88 million for that one. And previously, what was our best? 62 million. So we're a bit better for the best value for the move. So even the move is faster. And the distance from origin, 55 million, is much better than the StampedLock. And both are better than synchronized. Right, so we're out of time. If you have any questions, please come up and speak to me. Don't forget, this link is only going to be valid until 11 o'clock. After that, it's gone, right? So get it if you want it. If you don't want it, that's also cool. But we're happy for you to have it. Any questions, come speak to me. Thank you very much for listening.